Welcome to this problem walkthrough. Today, we'll explore a classic and commonly asked interview question, problem number 160, intersection of two linked lists. We'll break it down step by step, analyze different approaches, and understand the key concepts to solve it efficiently. Let's dive in. In this problem, we are tasked with determining the intersection point of two singly linked lists. You are given the heads of these two lists, head A and head B. If the two lists intersect, your goal is to return the node where the intersection begins. Otherwise, if there is no intersection, you should return null. It's important to note that the intersection is defined by reference, not by value. This means the intersecting node must be the exact same object in memory, not just a node with the same value. Additionally, the original structure of the linked lists must remain intact, and you can assume there are no cycles in either list. The solution must be efficient, with a time complexity of O, n plus m, where n and m are the lengths of the two lists, and a space complexity of O, 1, meaning you cannot use any extra space proportional to the input size. The input consists of the two head nodes, and the output will either be the intersecting node or null if no intersection exists. Let's look at an example to understand the problem better. Suppose we have two linked lists. List A contains the nodes 4-1-8-4-5, and list B contains the nodes 5-6-1-8-4-5. The two lists intersect at the node with the value 8. This means the node with value 8 exists in both lists as the exact same node by reference. The function should return this intersecting node, and the output for this example would be intersected at 8. The structure of the list shows that all nodes following the intersection point, including the 8 itself, are shared between the two lists. Here's another example. In this case, list A contains the nodes 1-9-1-2-4, and list B contains the nodes 3-2-4. The intersection begins at the node with the value 2. Again, it's important to highlight that the node with value 2 is the exact same object in memory, meaning it is shared between the two lists. The function should return this node as the intersection point, and the output will be intersected at 2. Now consider another scenario where list A contains the nodes 2-6-4, and list B contains 1-5. In this case, the two lists do not intersect at all. Since there's no shared node, the function should return null. For the scenario where the two lists do not intersect, the output is simply null. This shows that the function needs to handle cases where the two lists are entirely separate and have no nodes in common. Now let's go over some constraints and edge cases. The number of nodes in each list can range from 1 to 10,000, and the value of each node can range from 1 to 100,000. The lists may or may not intersect, and they will not contain any cycles. Some edge cases to consider include situations where the lists do not intersect at all, where the lists are of very different lengths, or where one of the lists is empty, making an intersection impossible. Another edge case is when the intersection occurs at the very first node of one or both lists. An additional edge case to consider is when both lists consist of a single node, and that node is the same by reference. In this scenario, the single node is also the intersection point. This highlights the importance of checking for shared nodes even in the simplest cases. These edge cases ensure that our solution is robust and handles all possible inputs effectively. To solve the problem of finding the intersection of two linked lists, the brute force approach is the most intuitive but also the least efficient. Here, we compare every node in the first linked list with every node in the second linked list. This means for each node in the first list, we iterate through all the nodes in the second list to see if they reference the same memory location. If we find a match, that node is returned as the intersection. If no match is found after checking all nodes in both lists, we return null. While this method is easy to understand and implement, its time complexity is O, m*n, where m and n are the lengths of the two lists. This is because every node in one list is compared against every node in the other. Additionally, it has a space complexity of O, 1, since it doesn't use any additional data structures. The trade-off here is that this approach becomes impractical for larger lists due to its inefficiency, as the number of comparisons grows rapidly with the size of the lists. A more efficient solution is the two-pointer technique, which cleverly synchronizes the traversal of the two linked lists. The main idea here is to align the pointers for both lists by redirecting them when they reach the end of their respective lists. Two pointers, PA and PB, are initialized at the heads of the two lists. When a pointer reaches the end of its list, it is redirected to the head of the other list. This ensures that both pointers traverse the same total number of nodes, regardless of the differing lengths of the lists. Eventually, the pointers will either meet at the intersection node or both reach null if there is no intersection. This approach has a time complexity of O(m plus n), as each pointer traverses each listed most once, and it uses O(1) space since no additional memory is required. While it requires careful pointer manipulation, this method is highly efficient and seamlessly handles varying list lengths without extra calculations. Another approach to solving this problem is by using a hash set. The intuition here is to leverage the properties of a set to quickly check for shared nodes between the two lists. First, we traverse the first linked list and store each node in a hash set. Then, we traverse the second list and check if any of its nodes exist in the hash set. If a match is found, that node is the intersection and is returned. If no match is found after traversing both lists, we return null. This method has a time complexity of O(m plus n), since each list is traversed once, but it requires additional space of O(m) or O(n) to store the nodes in the hash set. While this approach is straightforward and avoids the potential pitfalls of pointer manipulation, the additional memory usage can be a drawback for scenarios where memory is constrained or the lists are very large. Of the approaches considered, the two-pointer technique stands out as the best choice for its efficiency and simplicity. With a time complexity of O(m plus n) and a space complexity of O(1), it scales well even for large linked lists. Unlike the brute force approach, it avoids unnecessary comparisons, and unlike the hash set approach, it doesn't require additional memory. The key insight here is that redirecting the pointers when they reach the end of their respective lists allows them to traverse the same total number of nodes, aligning them perfectly for a synchronized comparison. This eliminates the need to manually calculate or adjust for the difference in list lengths. While it does require careful implementation to handle the pointer manipulation correctly, this trade-off is more than worthwhile given its optimal performance and elegance. The final recommendation is to use the two-pointer technique for solving this problem. It offers the most balanced and efficient solution, combining simplicity with optimal performance. By avoiding the inefficiencies of the brute force method and the memory overhead of the hash set approach, it provides an elegant way to tackle the problem of finding the intersection of two linked lists. This makes it the ideal choice for both small and large datasets. The problem we're tackling here is to find the intersection of two singly linked lists, if one exists. By intersection, we mean the node where the two lists start to share the same reference in memory. This is not based on the value of the node, but rather the reference itself. If there's no intersection, the result should be null. Now, let's start with the brute force approach. First, we initialize two pointers. PTRA starts at the head of the first list, head A, and PTRB starts at the head of the second list, head B. The idea is to use PTRA to traverse every node in the first list. For each node PTRA points to, we reset PTRB to the beginning of the second list, head B, and traverse through it node by node. During this traversal, we compare the nodes PTRA and PTRB by their references. If we find a match, meaning the references are the same, we return that node as the intersection point. If the entire traversal completes without finding a matching node, we return null, indicating that the two lists do not intersect. The brute force approach is straightforward but inefficient. It compares every node in the first list against every node in the second list, leading to a time complexity of O(m*n), where m and n are the lengths of the two lists. However, it does have a space complexity of O(1), as it doesn't require any additional data structures. To improve efficiency, we can use the optimized two-pointer technique. First, we check for edge cases. If either of the lists is empty, represented by head A or head B being null, we immediately return null since an intersection isn't possible. Then, we initialize two pointers, PTRA and PTRB, at the heads of the two lists, head A and head B, respectively. Next, we traverse both lists simultaneously using the two pointers. Each pointer moves one node at a time. When a pointer reaches the end of its list, it's redirected to the head of the opposite list. For example, if PTRA reaches the end of head A, it is set to head B, and similarly, if PTRB reaches the end of head B, it is set to head A. This redirection ensures that both pointers traverse an equal total distance, regardless of the lengths of the two lists. The traversal continues until the two pointers either meet at the intersection node or both reach the end of their respective lists, which means there is no intersection. This approach is efficient because it synchronizes the pointers, ensuring that they meet at the intersection after traversing the same combined distance. The time complexity is reduced to O, m plus n, and the space complexity remains O, 1. The algorithm relies on two primary data structures, the linked list nodes themselves and the two pointers used for traversal. The key here is the reference comparison between nodes, which allows us to determine if two nodes are the same. Several edge cases must also be considered. If the lists do not intersect, the pointers will eventually both reach null, and the loop will terminate without finding an intersection. If one of the lists is empty, the algorithm immediately returns null, as no intersection is possible. If the intersection occurs at the very head of the lists, the algorithm will detect it during the first comparison of PTR-A and PTR-B. The two-pointer technique significantly optimizes the solution by avoiding nested loops and reducing the time complexity to O, m plus n, while maintaining space efficiency with O, 1, auxiliary space. Let's walk through an example to see how the two-pointer technique works. Consider two linked lists, list A is 1 2 3 4 5, and list B is 6 7 4 5. The intersection occurs at node 4. Initially, PTR-A starts at 1, and PTR-B starts at 6. As we traverse the lists, PTR-A moves through 1 2 3 4 5, then switches to list B, proceeding through 6 7 4. Similarly, PTR-B moves through 6 7 4 5, then switches to list A, proceeding through 1 2 3 4. Both pointers eventually meet at node 4, which is the intersection point. The algorithm then returns this node as the result. If no intersection existed, both pointers would reach null, and the algorithm would return null. This example highlights how the two-pointer technique ensures both time and space efficiency while solving the problem effectively. This implementation solves LeetCode problem number 160, intersection of two linked lists efficiently using a two-pointer approach. Here's a breakdown of the code. 1. List node class. This is a basic definition of a node in a singly linked list. Each node contains a value, val, and a reference to the next node, next. This is standard for linked list problems on LeetCode. 2. Edge case handling. At the beginning of the getIntersectionNode method, we check if either head A or head B is none. If so, there's no intersection, and we return none immediately. 3. Pointer initialization. Two pointers, pointer A and pointer B, are initialized to point to the heads of the two linked lists, head A and head B respectively. These pointers will traverse the lists to find the intersection. For two-pointer traversal, the key logic lies in the while loop. The pointers traverse their respective lists and switch to the head of the other list if they reach the end of their own list. This ensures that both pointers traverse the same total length, which includes the combined lengths of the two lists. If there's an intersection, the pointers will meet at the intersection node during this traversal. If there's no intersection, both pointers will eventually become none at the same time, exiting the loop. 5. Return the intersection node. If the pointers meet, they point to the intersection node, which is returned. If no intersection exists, the loop exits with both pointers being none, and none is returned. This approach has a time complexity of O, m plus n, where m and n are the lengths of the two linked lists, as each pointer traverses each list at most once. The space complexity is O, 1, as it uses only two pointers and no additional data structures. This solution is efficient and elegant, avoiding the need for additional memory or modifications to the input lists while ensuring correctness for all edge cases. Here, we start by defining the structure of a linked list node using the listNode class. Each node contains an integer value and a reference to the next node. In the solution class, we implement the getIntersectionNode method to find the intersection of two linked lists. First, we check if either list is null. If so, there's no intersection, and we return null immediately. Next, we initialize two pointers, pointer A and pointer B, to traverse the two linked lists starting from their respective heads. The key idea here is that as these pointers traverse the lists, they will eventually align by switching to the head of the opposite list when they reach the end of their current list. This ensures that both pointers traverse the same total length, even if the lists themselves have different lengths. The while loop continues until pointer A and pointer B meet, meaning they point to the same node or both become null if there's no intersection. The logic ensures that both pointers either meet at the intersection node or simultaneously reach the end of the lists without finding an intersection. Finally, once the loop exits, we return pointer A, which will either be the intersection node or null if no intersection exists. This approach is efficient in terms of time complexity, as it traverses each list at most twice, and it doesn't require extra memory for additional data structures. Here, we have two linked lists, list A and list B, that intersect at the node with the value 8. To find this intersection, we use two pointers, pointer A and pointer B, starting at the heads of their respective lists. Initially, pointer A points to 4 in list A and pointer B points to 5 in list B. In the first iteration, both pointers move to the next node, pointer A goes to 1, and pointer B moves to 6. As they continue to iterate through their respective lists, pointer A progresses through 8, 4, and 5 in subsequent steps, while pointer B traverses 1, 8, and 4. When pointer A reaches the end of list A, it resets to the head of list B, starting again at 5. This switching mechanism is key to aligning the traversal paths of the two pointers, allowing them to eventually meet at the intersection node if one exists. After pointer A resets to the head of list B, pointer B continues its traversal and eventually reaches the end of list B, at which point it resets to the head of list A. In the next iterations, both pointers move step by step, aligning their paths. Pointer A moves from 5 to 6, while pointer B resets to 4 and progresses to 1. On the following iteration, both pointers move to the node with the value 8. At this point, since pointer A and pointer B are pointing to the same node, we identify this as the intersection node. The value of the intersecting node is 8, which is the result we return. In this example, we examine two linked lists that do not intersect. List A consists of the nodes 2, 6, and 4, while list B contains 1 and 5. As before, pointer A and pointer B start at the heads of their respective lists. In the first iteration, pointer A moves from 2 to 6, and pointer B moves from 1 to 5. On the second iteration, pointer A progresses to 4, while pointer B reaches the end of list B and resets to the head of list A, starting again at 2. Similarly, pointer A reaches the end of list A and resets to the head of list B, starting at 1, while pointer B continues to traverse list A. This process continues until both pointers traverse all nodes in both lists without finding a common node. Eventually, both pointers reach the end of their respective lists, at which point they both point to none. Since the pointers never meet at a common node, we conclude that there is no intersection between these two lists. Additionally, in the case where one or both lists are empty, such as list A being empty while list B contains nodes 1, 2, and 3, the process is straightforward. Here, pointer A is initialized to none since list A is empty, while pointer B starts at the head of list B. As pointer A is already none, the function immediately determines that no intersection exists and returns none as the result. The two-pointer technique used in this solution relies on several key observations. First, by traversing both lists completely, the pointers effectively equalize their traversal lengths, ensuring that they either meet at the intersection node or both reach none if no intersection exists. This approach guarantees convergence in O, m plus n, time, where m and n are the lengths of the two lists. Importantly, the space complexity is O(1), as the algorithm uses only two pointers without requiring additional data structures. This makes it a highly efficient and elegant solution to the problem of finding the intersection of two linked lists. The time complexity of this algorithm is O, m plus n, where m is the length of linked list A and n is the length of linked list B. To break it down, initializing the two pointers, pointer A and pointer B, is a constant time operation, contributing O(1). The main traversal of the two lists is the key contributor to the time complexity. In the worst-case scenario, each pointer traverses its own list fully, then switches to the other list and traverses it as well. This totals m plus n steps. The switching mechanism ensures that both pointers account for any difference in the lengths of the two lists and guarantees that they meet at the intersection node or both reach the ends simultaneously. During this traversal, the comparison of nodes at each step is a constant time operation, O(1), per comparison. Combining these factors, the overall time complexity of the algorithm is O, m plus n. The space complexity of this solution is O(1), which means it uses a constant amount of memory regardless of the size of the input lists. This efficiency is achieved by using only two pointers, pointer A and pointer B, to traverse the lists. These pointers occupy a fixed amount of memory, irrespective of the lengths of the linked lists. Importantly, the algorithm does not require any additional data structures, such as arrays, hash tables, or recursion, which could increase memory usage. The memory overhead is limited to the 2 pointers, making the space complexity constant, O1. When analyzing the algorithm under different scenarios, we see varying performance. In the best case, if the heads of the 2 linked lists are the same, the algorithm terminates immediately after one comparison, resulting in a time complexity of O1. In the average case, the pointers typically traverse portions of both lists before meeting at the intersection node, which gives a time complexity of O(m plus n). In the worst case, if the 2 lists do not intersect, each pointer traverses both lists fully, resulting in the same time complexity of O(m plus n). Comparing this solution to a brute force approach highlights its efficiency. A brute force method would compare every node in list A to every node in list B, resulting in a time complexity of O(m*n). While both approaches have the same space complexity of O1, the current solution is far superior in terms of time complexity, especially for larger lists, as it avoids the inefficiencies of nested comparisons. To mathematically justify the O(m plus n) time complexity, consider the traversal steps of the 2 pointers. Initially, pointer A traverses all m nodes of list A, while pointer B traverses all n nodes of list B. When a pointer reaches the end of its respective list, it switches to the head of the other list. This ensures that both pointers traverse the same total distance of m plus n. If the 2 lists intersect, the pointers meet at the intersection node within this total traversal. If they do not intersect, both pointers reach the end of their respective lists simultaneously after m plus n steps. Importantly, each step of the traversal involves a constant time operation, such as moving the pointer or comparing nodes. This guarantees that the algorithm completes in O(m plus n) time. When tackling linked list problems, there are a few common pitfalls to watch out for. One big mistake is not handling edge cases, such as when one or both linked lists are empty. If you don't check for null values explicitly, you might run into null pointer exceptions or incorrect results because the code assumes the lists aren't empty. Another issue is relying on inefficient brute force techniques, like using nested loops, especially when dealing with large inputs where each list could have tens of thousands of nodes. This approach can drastically slow down your solution and even cause timeouts. Instead, focus on optimizing with methods like hashing or the 2-pointer technique to improve efficiency. Additionally, pointer updates are a common area of errors. Forgetting to properly update pointers, such as using current.next incorrectly or missing updates altogether, can lead to infinite loops or crashes. Lastly, it's critical to understand how intersecting linked lists share memory. Many assume that the lists only share values, but the nodes after the intersection point are actually the same in memory. Neglecting this detail can result in incorrect solutions, so always account for shared memory when solving these problems. Another common mistake is misinterpreting the problem constraints. For example, if the problem specifies that the lists are sorted or guarantees no cycles, overlooking these details can lead to overly complex or incorrect solutions. Always take time to carefully read and leverage the constraints to simplify your approach. Speaking of interviews, there are a few strategies that can help. First, recognizing patterns in linked list problems, such as the use of fast and slow pointers or leveraging hash sets, can save you a lot of time. Next, don't hesitate to clarify requirements, particularly edge cases like empty lists or cyclic structures, to ensure you fully understand the problem. Be ready to discuss trade-offs as well. Interviewers often appreciate when you explain why you chose a specific method and how it compares to alternatives in terms of time and space complexity. Finally, drawing diagrams is an invaluable tool for linked list problems. Visualizing the process helps you avoid mistakes with pointer manipulation and also makes it easier for the interviewer to follow your thought process. To deepen your understanding of linked list problems, you might want to explore related challenges. For example, LeetCode 160, the problem we're discussing, focuses on finding the intersection of 2 linked lists. LeetCode 141 and 142 deal with detecting cycles in linked lists, while LeetCode 876 helps you practice finding the middle node of a list. These problems often share similar techniques, so solving them can build your intuition. Now, let's talk about alternative approaches. One option is the hash set approach. The idea here is to store all the nodes from one list in a hash set, and then traverse the second list to find the first node that's already in the set. This gives you an O(n) time complexity, but at the cost of O(n) space. It's faster than brute force and relatively straightforward to implement, but it's not the most space-efficient solution. Understanding these trade-offs is crucial in choosing the right approach for a given situation. Another highly effective method is the two-pointer technique. Here, you use 2 pointers to traverse the lists. When one pointer reaches the end of a list, it's reset to the head of the other list. This ensures that both pointers eventually meet at the intersection point. This approach is optimal with O(n) time complexity and O(1) space, but it does require a solid understanding of how the logic works. Another intuitive approach is to calculate the lengths of both lists and adjust for the difference by skipping extra nodes in the longer list. Once both lists are aligned, you traverse them together to find the intersection. This method is also O(n) in time and O(1) in space, and while it's straightforward, it does require an extra pass to compute the lengths. Ultimately, for intersection problems, it's vital to remember that the two lists share memory beyond the intersection point. Use the problem constraints to guide your approach, and aim for solutions that optimize for both time and space. Interviewers often value a well-balanced and efficient solution. Great job reaching the end. To wrap up, we covered how to solve the intersection of two linked lists problem using both brute force and optimized approaches. Remember, the key takeaway here is the pointer alignment technique, which is a must-know for technical interviews. Thanks for watching, and be sure to stay tuned for more coding tutorials and problem-solving tips. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!